Okay. 3.37, we're being asked a bunch of stuff. Let's focus on the very first thing. So we are being asked to prove equation right here using equation 3.73. So equation 3.73 is relating the rate of change with respect to time of the expectation value of an operator to the Hamiltonian. So if we have a d by dt of an expectation value of q hat here, and we have a d by dt value of q hat where q hat is xp, let's just substitute xp into q hat and see where that takes us, right? So if we write in xp, then now we have d by dt of xp is going to equal I over h bar, expectation of the commutator of the Hamiltonian with xp, or x hat p hat now, added with the partial with respect to time of x hat p hat. Okay, so immediately one thing you can do to instantly simplify this is you could recognize that, hey, in x space, I know that x hat is equal to x, and I know that p hat is equal to negative I h bar d by dx. Neither of these have an explicit time dependence, and I just realized that I wrote this as d by dx instead of d by dp. There we go. Okay, so neither of these have a t variable inside of them, right? Neither of them have an explicit dependence on time. So therefore, if you take a derivative of them with respect to the variable time, which they don't have any dependencies on, this automatically goes to 0, so we can ignore it. What we actually care about is, therefore, this expression. Okay, so this is going to end up being kind of a messy thing because we're going to have to fully expand this out, right? Because this is a commutator that we have to evaluate and somehow show that it simplifies down to this expression. So to do that, we're going to have to rewrite the Hamiltonian and all that stuff into x operators. We have to rewrite p into an x operator. We have to rewrite h into an x operator. We've done that for p. That's easy. The Hamiltonian is a little bit more complicated. We know that the Hamiltonian is equal to p hat squared divided by 2m plus the potential energy of the system v of x comma t. Okay, rewriting this again, this time plugging in p hat in terms of x. This is going to give me, let's see, 2 negatives make a positive, 2 i's make a third negative, so negative h bar squared over 2m d2 by dx squared plus v of x comma t. Okay, in that case, the commutator of h hat with x hat p hat, I wrote this wrong, it should be commutator, not expectation. This thing is going to equal h hat, x hat, p hat minus x hat, p hat, h hat. Okay, in that case, if we write everything out, this is going to equal, let me just copy paste all of this over. X hat negative I h bar d by dx minus x hat negative I h bar d by dx, and then this thing. Okay, let's simplify a little bit, right? Negative I h bar can go to the front, so now you have negative I h bar, then this same expression here, multiplied by x, because x hat just becomes x, d by dx, subtracted. The two negatives make a positive. Once again, I h bar moves out, so plus I h bar x d by dx of this same expression. Okay, now, in order to actually do, or in order to actually calculate a commutator, we're going to have it apply onto a function, right? So if we write out this entire thing, the expectation value can now be expanded out to be an integral from negative infinity to infinity of psi star, and then this whole thing, but acting on psi, right? So let me see if I can write out this whole thing. This right here let's just wall this off like that, and then you have a psi right here. Oh, that's kind of a messy psi. A psi right here, and then plus, and here we're going to do some we're going to do some distributive property here. This becomes d2 with respect to psi, not psi squared, plus v of x comma t times psi of x comma t, like that. And then this whole thing is getting closed off with the dx at the end. Like that. Okay, so what we basically did is that we took, you know, the psi that normally goes to the right, and then we distributed it into each of these two individual expressions, because really you're looking at two expressions. This is the first one and this is the second one, right? So in order to avoid, you know, filling up the entire screen, let's work on these separately. So let's start with expression 1. So you have negative I h bar, negative h bar squared over 2m d2 by dx squared plus v of x comma t times x d psi by dx. Okay, we're going to have to apply this d psi by dx onto each of these two expressions in here. So we have negative I h bar, and now let's see, negative h bar squared over 2m. And actually, you know what? I don't like writing this entire expression out, so let's distribute the negative I h bar into each of these. So we have positive I h bar cubed over 2m d2 by dx squared of x d psi by dx minus I h bar, and then there's no derivative here, so v x d psi by dx, just like that. Okay, let's do chain rule onto this expression. What is happening? Okay, there we go. Sorry, my colors were being messed up there. This expression goes to d by dx of box prime times triangle. So d psi by dx plus triangle prime times box, d2 psi by dx squared times x, box prime times triangle plus triangle prime times box. Yeah. Do it again. You get d2 psi by dx squared plus box prime d3 psi by dx cubed times triangle plus triangle prime times box, d2 psi by dx squared. The left and the right terms combine, you get 2d squared d2 psi by dx squared plus d3 psi by dx cubed times x. Okay, now if we plug that back in, we have distributing this in, I h bar cubed over m times d2 psi by dx squared plus I h bar cubed over 2m d3 psi by dx cubed times x subtracted by I h bar v times x d psi by dx. Okay, now let's do the second expression. I think I'll do it to the right here. Okay, so we have I h bar x d by dx of negative h bar squared over 2m d2 psi, d2 psi by dx squared plus v of x comma t times psi of x comma t. Okay, so this expression is going into both of these, right? So this is going to give us, let's see, I h bar x negative h bar squared over 2m, and then d3 psi by dx cubed, and then plus I h bar x box prime times triangle. That's going to be dv by dx times psi plus triangle prime times box, d psi by dx times v, like that. Okay, let's simplify out a few expressions. This becomes negative I h bar cubed over 2m times x d3 psi by dx cubed. And then expanding this out, this gets plus I h bar x dv by dx times psi plus I h bar x d psi by dx times v. Okay. Now the question is there anything that we can cancel? So immediately I see this expression, and this is the exact opposite of this expression. So that means these two can go. I h bar v, I h bar vx, I h bar vx d psi. Okay, these two are also exact opposites, so these two can also go. So this cancels with this, and what we're left with is two smaller expressions. And now what we have is that same d by dt expression closed off with I h bar cubed over m d2 psi by dx squared, and then the green expression plus I h bar x dv by dx times psi of x comma t. Okay, and now what we can do is we can turn this back into a standard expectation value expression by moving the psi back out to the right. So this is going to become, let's actually write this out because this is gonna cause some offsets. I h bar cubed over m d2 by dx squared plus I h bar x dv by dx, like that, and then we move the psi back out. So this expression here is the commutator of h hat with xp, or x hat p hat, I suppose. And remember, our ultimate goal is we want to show that it simplifies out to this, right? So somehow we want to show that this expression right here, whoa, that's a, okay, there we go. Somehow we want to show that this expression right here is going to simplify down to this. So what do we have? There's a few things that we can immediately do. Because if you look here, we have an expectation value of x dv by dx. That's this. So if we factor out the I h bar, then that's half our problem solved already. So let's do that first. If we get rid of the I h bar, move it outside, then this is going to give us two i's make a negative, and then the h bar cancels. So negative integral negative infinity to positive infinity of psi star h bar squared over m d2 by dx squared plus x dv by dx psi x, well, I don't think I need that anymore, dx, like this, right? So this can then be split via distributive property into two individual expressions, right? Because this is equal to negative of the expectation value of h bar squared over m d2 by dx squared plus the expectation value of x dv by dx, like that. So the question now is, how are we going to turn this expression into something that looks like 2 times t. We're also missing a negative sign, which makes me think that maybe I have done something wrong. Oh, okay. Actually, I didn't do anything wrong at all. It's the only thing I missed is this is supposed to be a negative in front of an entire expression like that. So the negative distributes in. Like this. Right, because this negative is originally in front of the entire integral. So when you split the integral into 2, the negative still applies to both terms. So then you distribute out the negative and you distribute it back in like this and you get this. Okay, there we go. That's more in line with what we want. So what we have now is if we move the negative on the first side back in, we have negative h bar squared over m d2 by dx squared minus expectation x dv by dx. So this term is already in the form of what we want. What we have to do now is we have to turn this back into something that looks like t. Now, if you think about t, right, t is kinetic energy, mass times velocity squared. We can also relate it in terms of momentum, right, because we know that momentum is equal to mass times velocity, so p squared is equal to mass squared times velocity squared. Therefore, t is equal to p squared over 2m, right? In that case, if we can relate t to p, well, we have something here that looks like it's a p squared, right? Because we know that p hat, let's write this in blue, we know that p hat is equal to negative I h bar d by dx. So that means that p hat squared is equal to negative h bar squared d2 by dx squared. So right here we have negative h bar squared d2 by dx squared. So this is actually equal to p hat squared divided by m. Okay, well, p hat squared divided by m is just equal to 2 times t. So therefore this can be substituted in as 2t. And at this point, this is just going to, the 2 is going to come out and we have 2 times the expectation of t minus expectation of x dv by dx. And that is what we were looking for at the start. So that is going to take care of the first part of this problem. Now, let's look at the second part. In a stationary state, the left side is 0. Why? Okay, so let's look at a stationary state, right? By definition, a stationary state has its positional component and its time component as separate expressions multiplied together. So in a stationary state, we have psi n of x comma t is equal to little psi n of x plus little phi n of t, where phi n of t has been defined explicitly as the complex exponential of e to the negative I e n times t divided by h bar, where n is a given energy state, right? Okay, so hypothetically, if we were to plug this in for the virial theorem, or we haven't gotten to the virial theorem yet actually, but if we were to plug this in for the d by dt expression we had earlier, right? This is equal to d by dt of the integral from negative infinity to positive infinity of psi. Well, actually, you know what, before that, I think I might be skipping too many steps. Let me try to explain this really quick. So, in a stationary state, the left side is 0. So, right now we have d by dt, that is written horribly, d by dt of xp is equal to this expression. We want to show now that somehow d by dt of xp is equal to 0. So how do we show this for a stationary state? Well, let's write out what the actual expression for an expectation value looks like. D by dt of the integral from negative infinity to positive infinity of psi n star x e to the positive I e n t divided by h bar x hat p hat, and then, well, actually let's write this as the actual operator itself. So this is going to be x times negative x I h bar d by dx of psi n of x times e to the negative I e n times t divided by h bar, where it's acting on this entire thing. Now, immediately, there is no x dependency for the complex exponential, so this thing immediately cancels out with this thing, right? So now what you have is d by dt of the integral from negative infinity to positive infinity of psi n star x times negative x I h bar d by dx of psi n of x, like this, right? Okay, so in that case, what we can do now is we can plug this in, right? So this is going to give us negative infinity to positive infinity psi n star of x negative x, and we're going to actually move I h bar out, times d psi by dx, like this, right? And we close this off with a dx. So what you have here is this expression is purely an expression in terms of x. There is no time dependency anywhere, and you are trying to take the time-based derivative of this function that is purely in terms of position, which means that d by dt of whatever this function ends up being is ultimately going to equal 0. Therefore, d by dt of xp is going to equal 0. So, because of that, this original expression that we had, whoa, I just cut it, whoops. This original expression that we had, automatically, because the left side is equal to 0, we can now move this to the left, and now we have 2 times the expectation value of t is equal to the expectation value of x dv by dx. Okay, that's the second part of this problem solved. Let me increase the size of my canvas really quickly. Okay, now the third part of our problem. So we have established the virial theorem, which is specifically true for stationary states, right? We want to use it to prove that the expectation value of t is equal to the expectation value of v for stationary states of the harmonic oscillator. And then furthermore, we want to check that this is actually consistent with the results that we got in an earlier set of problems, 2.11 and 2.12. So let's look at this. So for a simple harmonic oscillator, we want to show that the expectation value of t is equal to the expectation value of v. Now, the simple harmonic oscillator is a stationary state, so for a simple harmonic oscillator, we know that this expression is still true. So we want to somehow take this expression and simplify it down to this. So how do we do that, right? What do we know about a simple harmonic oscillator? Do we know what the kinetic energy is? Because really we're working with two expressions, right? We're working with t and we're working with v, which is kinetic energy of the simple harmonic oscillator and the potential energy of the simple harmonic oscillator. Here, somehow the potential energy is able to be expressed in terms of x. So immediately that should make you think, okay, well, I know that the potential energy of a simple harmonic oscillator is 1/2 kx squared, or 1/2 m omega squared x squared. Doesn't really matter which one you use. I like to use this one, so I'll use this one. If I say that, okay, then in that case, I know that 2t is equal to x d by dx of 1/2 m omega squared x squared. If I derive this with respect to x, then I get 2t is equal to x times, let's see, the 2 comes down, m omega squared x, right? In which case 2t is equal to m omega squared x squared, like this. Okay. At this point, I can take the 2 and I can move it to the right, right? Because this is just twice the potential of V. So T is therefore equal to 1/2 m omega squared x squared. And if you look at that, we're back up to here. This simplifies out to V, so therefore the expectation value of the kinetic energy is equal to the expectation value of the potential energy for our simple harmonic oscillator. Okay, next you want to show that the results you got in problem 2.11 and 2.12 are consistent with the result you get right here, which is that the expectation value of T is equal to the expectation value of V. So to show that, you can basically say, okay, well, back in 2.11 and 2.12, what we solved in that set of problems was how to create a formula for the expectation value of x, x squared, p, and p squared for the simple harmonic oscillator for any given energy state n. And what you found in 2.11 and 2.12 was basically that the expectation value of x squared is equal to h bar over 2m omega times 2n plus 1, and the expectation value of p squared was equal to h bar m omega over 2 times 2n plus 1, where both of these are for psi n of the simple harmonic oscillator. So if we know this, well, we can rewrite this in terms of x squared and p squared, right? Because we know that t squared, or not t squared, t is equal to p squared over 2m, and we know that v is equal to 1/2 m omega squared x squared, right? So in that case, by this rule, the expectation, I didn't want to cross that out, the expectation value of p squared times 1 over 2m should equal the expectation value of x squared times m omega squared over 2, right? So is that true? Well, let's plug this in. We have h bar m omega over 2 times 2n plus 1 times 1 over 2m on the left. And then we have being equal to h bar over 2m omega times 2n plus 1 multiplied by m omega squared over 2. Okay, so do these equal? On the left side, you have h bar m omega over 4m, so the m's cancel. H bar omega over 4 times 2n plus 1. On the right, you have h bar omega, because the m omega cancels the m omega squared, over 4 times 2n plus 1. Okay, so these two terms equal each other on the left and right side, therefore this is true. So with that, we have shown that expectation value of t is equal to the expectation value of v, and we've shown that this is consistent with the results we got from problems 2.11 and 2.12. One final point that I sort of want to make is to sort of emphasize the significance of what this means, right? So we showed that for a simple harmonic oscillator, the expectation value of t is equal to the expectation value of v. What this is basically telling you is that for a harmonic oscillator spring system, on average, the average kinetic energy is equal to the average potential energy. And if you think about how a spring system actually oscillates, or any simple harmonic oscillator, right? Any sort of like a pendulum, for example, in classical mechanics, as it goes into motion, right? It periodically goes between some kinetic energy and some potential energy. So at some point, right, at the height of the trajectory of the pendulum, or at the max compression of the string, you have t is equal to 0, and V is equal to its max value. And then at the bottom of the pendulum, or when the spring is completely extended, you have a moment where T is equal to the max of the system and V is equal to 0, right? So as this object goes through simple harmonic motion, the potential energy and the kinetic energy regularly oscillate between their minimum and maximum values according to a sine wave. And if you remember ever treating simple harmonic oscillators in classical mechanics, you should remember that T and V sort of operate on the exact same formulas. They have the same form, right? 1/2 mv squared, 1/2 kx squared, 1/2 m omega squared x squared. I forgot to add the x squared here, where m omega squared is basically functioning as like a k, right? So this sort of makes sense from a classical mechanics standpoint, and here we are proving that the same thing applies if we look at a simple harmonic oscillator from a quantum mechanical standpoint. So this is a good thing, right? This is telling you that all of the math and all of the weird quantum mechanical BS that you've been working on is agreeing with stuff that you first observed way back in classical mechanics. And that's the final thing I wanted to sort of make a point of, is to make sure that you understand that the point of this exercise is to show you that, hey, once again, a lot of stuff in quantum mechanics, despite how unusual the math is and how unusual the perspective that you approach it from is, a lot of the stuff that you observe for idealized systems sort of agrees with the exact same stuff that you observed back in classical mechanics.